Rydberg molecule?
Well, first, I'd like to thank you for the invitation to come here and attend this meeting. It's also an opportunity to visit my alma mater, so that's kind of nice. Okay, what I'd like to do today is to talk about some of the work that's underway in the ultra-cold Rydberg lab at Rice University. And this group is directed by Tom Killian and myself. And the work I will describe represents the efforts of a lot of people. We have a number of students involved: Robert Brienza, Ilu, Chang Yuan, Sumia Kinungo, who is actually now a postdoc. And we've had tremendous valuable theoretical input from our collaborators at the Vienna Technical University, Shuhei Yoshida and Joachim Bergdorf. What I'd like to do today is discuss two separate experiments. The first one was a series of microwave spectroscopy experiments on high-end singlet strontium Rydberg states. And our idea here was to develop a self-consistent set of quantum defects characterized by the Rydberg-Ritz parameters for the low L states S, P, D, and F to allow calculations of transition frequencies between these levels at a part in 10 to the 7. A second series of independent experiments were optical spectroscopy of rotational states in 86 strontium ultra-long-range Rydberg molecules, which we excite in the ground V equals 0 vibrational state. When we create these, we find an unexpected dependence of the rotational structure that we see in the excitation spectrum on the presence of even a very weak magnetic field. So I'd like to start then by talking about our microwave spectroscopy measurements. And again, we're doing these at fairly high N. Now, as many of you here know, Rydberg atoms are providing a powerful platform for quantum computation, simulation, and sensing. Now, many of these applications involve coupled Rydberg levels, where you're exciting transitions between Rydberg levels. And our application that we're working on in our lab is to use Rydberg atoms as synthetic dimensions. Now, Tom Killian will say more about this tomorrow in his talk, but just to give you a brief overview, let's consider you have a Rydberg atom in which you've got a chain of Rydberg levels, an SP, SP, SP. We can drive these transitions with microwaves. So, and by varying the strength of the microwaves, you can either couple those levels very strongly or weakly, or strongly or weakly, strongly, weakly. So you can control the interaction between these levels. And this would sort of mimic the behavior of an electron in a molecule like polyacetylene, where you have alternating double, single, double, single, double, single, double singlet, whoops, double bonds, okay? Now, if I was an electron in here, I'd see strong tunneling, weak tunneling, strong tunneling, weak tunneling, strong tunneling. And that's essentially what we have. We have strong coupling, which would be at the analog of strong interactions, and then weak interaction would be weak tunneling, strong tunneling, weak tunneling, strong tunneling. So what we would have then in this Rydberg system is we'd have an analog in some sense of what an electron would do in this real space system here. Now, this is, in fact, a model that's called the SSH Hamiltonian, and we can do interesting things. We can vary the tunneling rates, we can vary the on-site potentials by detuning the Rydberg atoms, and explore some of its properties. It has some topologically protected states, H states under certain conditions. Now, our goal is ultimately to extend our measurements to many more levels, so you're becoming much more like a many-body system. And to do that, we have to avoid unintended consequences, such as spurious couplings between different levels. It might happen that if we have a single photon transition here, somewhere up here, it would drive a 2-photon transition. We want to make sure that doesn't happen because we get spurious couplings. So what we do is we do microwave spectroscopy on these levels. And we've studied NS to NP, ND to N-3F, and 2-photon NS to N plus 1S, and NS to ND transitions. Now, the level separations, in other words, the transition frequencies, are just given by the difference of the two binding energies, where this is the appropriate Rydberg constant mass corrected for 84. This is N effective, which is just N minus the quantum defect. And the quantum defect is usually characterized in terms of Rydberg-Ritz parameters, delta naught, delta 2, and delta 4. Now, values of these parameters have been reported earlier based on optically measured term energies by Vaillant et al. However, the problem was when we took these expressions and tried to predict transition frequencies, we got an error of up to 100 megahertz. I say that's not very much in a 20 gigahertz frequency band, but it is when you're considering microwave transitions where you can get 10 kilohertz resolution. So why do optical measurements not do so well? Well, there are a number of challenges. The term energies are limited by the uncertainties in the optical frequency measurement. What you do is you're basically measuring the sum of one or more photons to get up to the level that you're interested in. Now, having got the term value, if you want to get the quantum defect, you have to then reference that to the ionization potential, and those preferred values have changed over time. Furthermore, if you go up in N, if you've got a given uncertainty in your term value, you get an uncertainty in the quantum defect that increases as N cubed. Now, you can avoid all of these problems if you simply make accurate measurement of transition frequencies and then use a fitting procedure to minimize the energy difference between the measured and the predicted energy separations. So remember, these are the predicted energy separations. So the way we do this is we use this following apparatus shown here. We start out by creating a cloud of cold 84 strontium Rydberg atoms, and they're done using the usual cooling methods for strontium, where you have a broadband blue MOT and then a red chain narrow-line MOT. We then load those cold atoms into an optical dipole trap, and we end up with about 10 to the 5th atoms, densities of about 10 to the 11th, and temperatures of about 1 microkelvin. Now, we then create N singlet S0, N singlet D2 states by 2-photon excitation using 461 and 413 nanometer radiation. This radiation is provided by frequency double diode laser systems, and we can actually measure the frequencies to about 60 megahertz accuracy. We then irradiate the atoms by a K-band Hall antenna, and we're limited in our frequency span from about 13 megahertz, which is the low frequency cutoff of the horn, to about 26 megahertz, which is the best our frequency synthesizers can do. And then we detect the Rydberg atoms by selective field ionization, which you remember is state selective. And this is illustrated here. You take the atoms, you subject them to a time increasing electric field. Now, Rydberg atoms in different states ionize at different applied fields. So by looking at the time during the ramp at which ionization occurs, you can measure actually the field at which ionization occurs, which tells you the Rydberg atom that you actually happen to have. So here I show some selective field ionization spectrum. Here's the electron signal from field ionization as a function of electron arrival time when we're driving 56S to 57S transitions using a ramped electric field. This is the range of field strengths, in other words, times over which 56 atoms should ionize, the same for 57 here. So we start out and run the SFI spectrum, and you see that we get essentially all in the 56 level. As we increase the drive time, then what we see is we see a transition, moving it to the 57S level. And we keep driving, and by gosh, it goes the other way and then returns. You see a series of very nice Rabi oscillations. That's all well and good, but if you're going to do accurate measurements of Rydberg atom level separations, you've got to remember that Rydberg atoms are very sensitive to AC and DC start shifts. So we must work to eliminate these. Now, the AC start shifts are relatively straightforward to eliminate by use of a Ramsey technique. What we do is we start out by driving the atoms with a frequency that's not exactly tuned to the resonance. It's a little bit off. Then what we do is we use a Rabi oscillation to determine how long a drive we have to produce a pi/2 pulse. So we then apply a pi/2 microwave pulse. We allow the atoms to evolve then without any microwaves on, in other words, in the dark. Then we apply a second pi/2 pulse, and we monitor the final population distribution. And here are some data. When we're doing this, we're driving 58 to 59 S transitions here. And you see some very nice Ramsey oscillations. And their frequency is the difference between the frequency we're applying and the actual atomic transition frequency. We can test the method by using various detunings and seeing if I always get the same reproducible final frequency. And in fact, we do with the limits of plus or minus 5 kilohertz. And then you can say, well, is there another way to check this method? And the answer is yes. You just measure the transition frequency directly versus the microwave power and extrapolate back to 0 microwave power. The two agree very well. Whoops. The two agree very well. Now, the DC start shift's a little more tricky. What we showed here is the line shift that we'd expect as a function of DC applied field. And they, we're working at high end, they can be pretty big. They range from 50 kilohertz for S states in a field of 20 millivolts per centimeter up to 2 megahertz for F states. So we have to work really hard to minimize those offset fields. And we do that in the following way. We take advantage of the system of electrodes we have around the cloud of atoms. And by applying offset potentials to these, we can generate known offset fields in the interaction region. Okay. And then we look at the line center shift as a function of the differential plate voltage that we're applying to establish electric fields in certain directions. Okay. And what we observe is some nice quadratic behavior. The important thing to recognize, though, is the minimum is not when we've got 0 differential voltage applied. There's a small offset voltage that we're applying, and that corresponds to something like 4 millivolts per centimeter in this particular case. Then we can iterate this procedure along all 3 directions, and in that way we can iteratively null the electric field down to small values. We're confident we can get down to 5 millivolts per centimeter. We may do even better. Even if it is 5 millivolts per centimeter, however, it's still only a few tens of kilohertz in the transition frequency. So how do we do measurements? Well, we started out saying, well, look, we've measured the term values optically with our lasers. So why don't we start out by determining quantum defects from those values that we get? And remember, our wavelength measurements give us an optical frequency of about 100. Uncertainty about 100 megahertz. So what we did is we just take the ionization potential, subtract it from the 2 photon energies, and that gets you then from this you can get delta. Now, for the ionization energy, we based it on the most recent value of the ionization energy for 88 strontium, given by Couturier et al. And obviously, we then have to apply the isotope shift. Now, when we did this, we got quantum defects, which we were in about plus or minus 0.003, for the values that were predicted by the earlier Rydberg parameters determined by Vaillant et al. And in fact, they were consistent with our uncertainties in our optical measurements. However, now if you do it by microwave spectroscopy, what you do is, again, we've measured all these transition frequencies. And then we use those to generate an updated self-consistent set of Rydberg parameters that are completely independent of the final ionization energy. We minimize the sum of the squared residuals given here for all the states, where this is the actual measured energy separation, this is the predicted energy separation, and this is just a measure of how accurate the particular series of experimental data that we're using are. So again, for this, we use the expression I gave before, and to vary the delta as we go through the fit, we just use then the Rydberg expression. Now you look at this and you say, well, we're not going to be very sensitive to delta 2 and delta 4 because our measurements are at high n. So where this n squared and this n to the 4th become rather big. So to get good values of delta 2 and delta 4, you go back to earlier measurements at lower n, and you use the level separations between these measurements at lower n. So we also feed into our calculation the level separations measured at lower values of n, and that gives us a better estimate of delta 2 and delta 4. When you do that, you get a new set of parameters. Here, the old parameters of Valent et al. Here are new parameters. And you notice we're specifying them to a part in 10 to the 7th so that we can get our transition frequencies to kilohertz in gigahertz. Okay. And if you look, then we will get a global self-consistent fit to the data, self-consistent fit to the data. And here are the various drive frequencies predicted and measured as a function of n. And then we've got data here for several different transitions. And again, we're restricted in drive frequency ranges from about 13 to 26 megahertz. Now, the scale of this data doesn't really tell you too much about how good a fit is. So down here, I show the residuals. And now these residuals between the predictions and the measurements, this is a scale of 100 kilohertz. And you see that if there are no systematic trends and the residuals are better than 20 kilohertz. Now you say, oh, that's good. The values of delta naught should be particularly good at high end because our measurements are made at high end. And you can then take our measurements and say, well, let's see what predictions we might have at higher end. Now, there are some previous microwave studies we've done at Rice with Rydberg levels up in the range of 125 to 160. These are the transitions that were measured. These are the frequencies that were predicted. These are the measured ones. These were the predicted ones. And we were within a megahertz for all of them, which isn't bad when you consider that the experimental uncertainty in those measurements was about 2 megahertz. So it tells us that the quantum defects that we have got should work over a very large range of n. Now, having got the quantum defects, we can compare those to earlier measurements of the quantum defect. And I do this here for singlet S Rydberg states. Okay. So here's the quantum defect, and notice it's on a very, very tight scale. It only goes from 3.272 to 3.260. And this is gain n. Now, the red line is Valent's earlier fit. The black line is our new fit. And you see on high resolution that we actually do a better job of our data than the earlier data. Now, included on here are earlier measurements from other groups. And a couple of interesting things come to light. If one looks at these open circles here, the yellow diamonds, they're results that were obtained by Rydberg et al. some years ago. And they used the old value of the ionization limit to determine their quantum defects. Well, if we take those data and we correct them to the new series term limit, they actually move up here and fit very nicely with our data. Earlier data of Gain et al., if that's corrected, the gain fits very well. These measurements of Escherich, they just gave term values. They did not actually reference it to the ionization limit to get the quantum defects. But if you do that, you get good agreement here. These other data are earlier data from our lab, and those already used a higher ionization limit because we realized it needed it. Otherwise, you were getting systematic trends in the quantum defect out here. So I think you would say that we now have pretty good agreement with all the data when we make all the corrections. And I think it's a pretty good value for the update. Now we go on to the SP and D states. We get similarly good agreement. What I show here is the NP state quantum defect versus N. Again, our measurements are black. The earlier results are red. And again, very good agreement with our data. And again, if we take earlier data and we correct it for the new ionization limit, like these red dots move up to here, everything is in good accord. Same for D states. Everything moves into good accord. Here's data for F states. And again, remember, that's a very, very detailed scale. Now, here the situation is a little different because earlier measurements of F state quantum defects by both us and by Gallagher were actually based on the then assumed D state quantum defects. If we modify it to our new D state quantum defects, these earlier data, which were off our present line, move up into very nice agreement. So we have a very good set of updated parameters that will provide you an excellent measure of quantum defects and transition frequencies between SP, D, and F levels at high N, and there's a very good opportunity to extend them out to higher N where they continue to work, and they should work at somewhere lower N. So when we're planning experiments now involving coupled Rydberg levels, we should be able to identify accidental resonances fairly easily. Now, the second set of experiments that I want to talk about are some optical spectroscopy measurements we've been making on the creation of 86 strontium long-range Rydberg molecules. Now, Rydberg molecules have been around for quite a while. They were first predicted theoretically by Chris Green and associates way back in 2000. And I'm sure everybody's seen this picture. It's been published many, many times. And what this shows is the electron probability density distribution in a high L Rydberg molecule. And it's called the trilobite state. It's called the trilobite state for obvious reasons. Now, you create a Rydberg molecule, which really consists of a Rydberg atom with one or more ground state atoms embedded in the electron cloud. That embedding is very weakly bound, and they become weakly bound because of electron scattering. And electron scattering can be represented by a Fermi pseudopotential. And using that, you can calculate the effective molecular potential. And this is what we do here. So here is the effective molecular potential as a function of internuclear separation. And this is for a 34s triplet S1 ground state atom combination. And you see there are a whole lot of wiggles here. And that's simply reflecting the fact that that is the radial electron probability density distribution in the atom. And this potential will support a number of ground vibrational levels. The wave functions are shown here in different colors. The ground state is bound by about 20 megahertz. The others are bound by a few megahertz. So the binding is weak. So you can only study them then using cold atoms. Another interesting property is if you look at the wave function for the V equals 0 level, you see that it's strongly localized in near this outer well here at a distance which corresponds to about 1.8 n squared a naught. So it's out towards the classical turning point for an S state. Okay? Now, these unusual characteristics have resulted in multiple applications. So the first one is to remember that, look, the V equals 0 vibrational state is strongly localized. So if one wants to produce such a state, you have to have two atoms initially at the required separation. Now, if I vary n, I vary that required separation because the atom size is changing. So by looking at dimer production as a function of n, you get information about the correlations that are the atomic correlations then in the medium that you're looking in. So you can use that to study correlation effects and correlation functions. And if you get down with the right regime, you can see quantum statistics. And this is illustrated by some data here from our lab, in which we've measured two-body and three-body correlation functions as a function of R, where the R is the size of the atom over the de Broglie wavelength. And we've chosen a regime in which the de Broglie wavelength is becoming larger and larger and larger than the separation we're interested in. If you do that, then the effects of quantum statistics become important. And what you see is if you look at the for G2 of R as a function of internuclear separation for bosonic 84 strontium, you see it's going up. Our probability of creating molecules is getting more and more, and that's because those states bunch. Bosons tend to bunch. If you do the same thing for gas of spin polarized 87 fermion strontium, which are indistinguishable, then you see that it goes down because you've got Fermi repulsion. And if you look at three-body effects, then they're much more pronounced. The effect of nuclear spin effects become much more pronounced. And you see there's a dramatic increase in production if you're in the bosonic state, and a dramatic decrease here. Another thing you can do is you can actually get to a situation where the Rydberg atom is so big and the background gas is so dense, you can have hundreds of atoms inside the electron cloud. So now you're sort of getting a transition from few to many body regimes. And the atoms inside the atoms inside the Rydberg cloud are sort of being shepherded by this one electron that's going around and bound. And if you go into the limits of this, it has an effect of actually influencing the tail, and this was demonstrated to be an effect in the production of Rydberg polarions. Now, we're interested in the ultra long range molecular dimers of 86 strontium. And you say, why 86 strontium? Well, the thing about 86 strontium is that the S-wave scattering length is large. It's about 811 Bohr, as compared to, say, that for 84 strontium. And that is becoming comparable to the size of Rydberg atoms with intermediate values of air. So what this means is, remember that there's a node in the scattering wave function at about that distance where you have a scattering length, okay? And that means then that if you've got to have a transition from the scattering state to a bound state, if the wave function in the scattering state is small, that's going to turn off at least the S-wave channel. And this is manifested by the fact that when you do this, you see a rather strange line shape, okay? It's asymmetric. And this can be fit by a sum of different Lorentzians. And we interpret the fact that there are these things as having suppressed the formation of the ground vibrational state at n equals 0, and allowing us to see the higher rotational states that are being produced. And I just show here some more better resolution, more recent data, where again, we've now looked at the excitation spectrum, and it breaks down very nicely into 3 well-resolved peaks. Now, we assign this to the ground rotational state, the n equals 2 rotational state, the n equals 3 rotational state. You say, can we really do that? Is it legitimate? And the answer is yes. You can measure the separation between these 2 peaks, or those 2 peaks, and you can say, how well does that compare to what we would expect? And that's shown here. Here's the separation between the peaks. Here's the internuclear separation, in other words, which depends on n. Here are the calculated values. This is simply assuming a simple rigid rotor. That will be the rotational spacing. This is a more sophisticated calculation, which involves some quantum mechanics. But you see that the measured separation is in pretty good agreement with what we would expect. To go to the 0 to 3 transition, again, the same is true. Now, the interesting thing is this line shape looks very nice. But when we actually left in the magnetic field on one day, we discovered that the line shape is very sensitive to the presence of very small magnetic fields. And this is illustrated up here. Here is the situation again for n equals 29, when we have a half Gauss field on, and then it's getting bigger and bigger and bigger and bigger and bigger as we go through the pictures. Here you see, in this particular case, there's a little bit of n equals 0, a lot of n equals 2, a little bit of n equals 3. A bigger field now, n equals 0 and 2 are becoming comparable. Even bigger fields, n equals 3 is n equals 0 is taken over from n equals 2, and we get this cyclic behavior as we go on. Now, in these measurements, the magnetic field is in this direction. The 2 lasers propagate, they counter-propagate, and they're linearly polarized, one parallel to the magnetic field, one perpendicular to the magnetic field. Now, when you see strange behavior like this, the first thing you say is, uh-oh, must be an instrumental effect. So we did the same experiment with 84 strontium, and in fact, there was no change in the line shape. So the interesting thing we observed was that these n-level populations oscillate periodically with changing magnetic field. So what we did is we plot here those populations for n equals 29 and n equals 30 states as a function of the magnetic field. And what you see is that for the n equals 0 state, you see a kind of nice sinusoidal oscillation. You also see a nice sinusoidal kind of oscillation in n equals 2 state. But you notice they're antiphase. This goes down, this goes up. You do the same thing for 30s, and you see the phase is shifting. You still get this kind of oscillation, but in a different phase in the magnetic field strand. Okay, the period for these oscillations is about 3.5 Gauss. And another interesting thing is if you look at the total dimer signal, then it oscillates, and it oscillates in phase with this population of formation of n equals 0 states. Now, this magnetic field dependence was totally unexpected. We have no idea at the moment quite what is happening. We plan some future studies to see if we can figure it out. First thing to do is to try singlet dimers, so we don't have any net electron spin, see if that helps. And the other thing is to do some time dependencies and in how long we irradiate for, to see if we're creating some coherent superposition of rotational states that are evolving in time. But the key thing is, at the moment, we really don't have any explanation for this. So if anybody has any ideas and suggestions, we would welcome them. And with that, I quit. Thank you.
So thank you, Barry. Nice talk. So I should say, Larry, a few years ago, before he went to the US, he did his PhD here. And just coincidentally, he did his PhD in one of the labs that's now one of my labs. So it's a funny circular situation. So there's time for questions. So Matt,
really nice talk, Barry. I had a question about the first part on the measurements of the new measurements of the quantum details. Did you see any effect of interactions or because you have a reasonably dense gas in your dipole trap, so
it's only 10 to the 11th, remember. And we're typically creating only one Rydberg atom per shot.
Yeah, but when you're sensitive in kilohertz levels, you might still expect it to still be some modification that could be density dependent. Did you search for any?
We did not do that. We have not. We thought it would probably be low enough that we wouldn't have to worry too much. But yes, I mean, if we went to a really dense trap, then we would perhaps have to worry about that.
I like your connection of your Rydberg ladder to the SSH model. Now, in the SSH model, when we think about these topological states, I mean, what you have, I think, is something like more like a single particle that is hopping in this
Yes.
ladder. But in the SSH model, you work at half filling. And do you have any suggestion? I mean, how one could achieve that in such a situation?
I mean, all we've done so far is, I was showing you this out. Now, Tom tomorrow will talk about some dynamics experiments in which we create, one particular state and then watch it evolve between the other states. Is that kind of what you're talking about? Well,
because I think what you want to have is like a real many-body system. Right?
That's correct. That's why you really want to go to many levels, so you can sort of start seeing the proper emergence of the band structure.
It's still a single. I mean, if you look at the Hilbert space, I mean, that doesn't grow exponentially with a number of levels.
Yeah, but I'm not 100% sure I understand what you're saying, but we are doing some experiments now where we create a particular Rydberg level, and then we watch it evolve over all the other states as time goes by. So you sort of get the dynamics of the evolution of the system. So we'd set up that system, we'd excite 56. And then as a function of time, we'd look at how that population was going up and down in states. And Tom, I don't know where he is, but I presume that's in your talk, Tom.
Okay, I was like.
Yeah, I think it's always a very clear presentation. I was also interested in the first part concerning the spectroscopy of the single Rydberg series. I was wondering if you could compare for me or say a few words about the triplet series. Is it comparatively well known, or is it not done?
It's probably, again, we've done some studies with the triplet system, but we've not done sort of super accurate measurements looking to get rid of the stray fields. And the uncertainties we saw there were about the same value. In other words, we'd go for a particular transition, calculate it, and we'd be tens to hundreds of megahertz off. And then, we've got a 10 kilohertz band that you go searching. Where is it, Now we don't have to search. Typically, the line widths of these transitions will be 50 kilohertz because we have a 20 microsecond pulse. So you're on it. You may be a little bit off, but you're close enough that you're there. But it's a little more complicated for the triplet system, obviously, because there are more levels where you have magnetic fields and things. But we do have the transition frequencies, and from here on out, what we're going to do, because we're now working with the triplet system for the lattices, what we're going to do is just each time we find one, we'll just make an accurate measurement. It's very quick with this Rabi oscillation method, Ramsey oscillation method. It's very quick. It's not a measure varying laser, varying microwave powers and everything. It's just one measurement, you've got it.
I just have a technical question. So with all these microwaves in this electrode structure that's presumably on the kind of wavelength scale, do you have funny interference effects or standing waves? Or...
Undoubtedly. We're actually building a new apparatus to do these kinds of experiments, which basically has two very large glass windows and a minimal amount of metal inside it. So we can get a much better idea of what's going on. And we've done some modeling, and no matter what you do, even the glass windows cause reflections and standing waves. So it's very hard to get microwaves known inside a vacuum chamber. At present, we just shine them in, and we just turn up or down the amount of microwaves to get the transition frequencies we need.
Right.
It's purely empirical.
Sure. Any other questions? Okay, so if not now, it's the lunch break. So for now, I wouldn't, well, you could leave maybe some things that are not super valuable in here. I mean, I don't think people will come in here, but I don't want to take responsibility. But other